Simply put, Alaska is a challenging place to build homes. Due to its geographic location, it's considered a northern climate, and in various parts of the state, it's actually an extreme northern climate. And due to its large size, within the state, we have a variety of severe climates, from maritime Alaska, where we have wet weather and freezing weather, to the northern part of the state, where we have prolonged periods of extreme cold. And the Cold Climate Housing Research Center here in Fairbanks, Alaska, has been working on various home designs to find a home that can be built successfully in all parts of the state. And as part of this process, CCHRC has come up with what we call the integrated truss design. The idea is to build a home that's healthy, that's durable, that can be shipped affordably, that's easy to construct, and that will last a long time. And in this video, we are going to highlight some of the construction processes and try to give the viewer a general sense of what's involved in building the integrated truss house. So how did you guys square up the foundation?
Well, we knew based upon the plans what the width and length is. So we took those dimensions, we determined the square root and the hypotenuse of the square, and checked both corners. And also just a typical measuring the diagonals to see if it's square. It can be parallel, but in this case it is square.
And how are you guys keeping the trusses straight as they're going in then? Are the beams straight enough that you can measure off them, or are you guys running a reference line on the plates? Or?
Well, the beams were not installed by us, but they were installed correctly. They're level, they're plumb, they're fastened correctly. And all we did was make sure that first gable end is level and plumb. And then we keep our spacing on each concurrent one so that it all falls into place. Now periodically we'll check maybe every fourth or fifth one and make sure that we're still on track.
The first one is the hardest one because it has to be plumb and it has to be where it belongs. If the first one is wrong, the rest of them will be wrong. And so the first one is the most important to place.
If you got one or two lead people that know what they're doing, it's pretty much follow as you say, and they go pretty quick. So we'll probably get this set today, and we only started at lunchtime basically. So 5 hours, we'll have 21 trusses set. takes an experienced crane operator too. So. Give me half.
Half?
Give me half, please.
Here we're looking at an integrated truss frame. This house here was raised in a day. One thing here that is worth noting is the trusses are sitting on double top plates. The double top plates are through bolted through both plates through the flange and the I-beam, so you've got a really solid connection here. Later there will be seismic anchors, hangers coming into every truss. But what's really important is when you're laying out for the layout on top of the plates, it doesn't matter whether the beams themselves are square or parallel to one another. You must establish a right triangle square layout so that this gable truss here going in this direction is square to the long walls regardless of how it rests on the beams. To ensure that these trusses were set and that the building is square, a chalk line was snapped that is square to the front gable end. And the idea is if you snap a line using a 3-4-5 triangle square to that gable end down the entire length of one of the outer plates, then every truss that you set can be measured in to this line. You're not measuring to the edge of the plate, which may or may not be straight. You're actually measuring every truss as it's being set. And therefore, your walls will be perfectly straight and the structure will be square regardless of what the beams are doing underneath it. The structure isn't particularly stable until you get the roof sheathing on and start working on some of the other sheathing. So it's really important that you've got some temporary bracing in place to make sure everything is fully supported so the structure can't get knocked over by wind or get racked by people working on top of the roof or anything like that. It's always best if you can put a couple of opposing braces in. I would say like we've seen here, and perhaps a couple more on the outside. And then if you can brace the building from both sides like we see here, the braces go back out onto the deck. Right here next to the deck, we've got a diagonal brace that goes down to the plates. And right above that, we have another diagonal brace that carries on top of the roof from the corner directly above our brace down to the deck, all the way up to the peak of the roof. Once again, that's reinforcing that stiffness. In addition, we've also used Simpson truss braces. These are 22.5 inches between the tabs. And when setting the trusses, these can be dropped in, and if they're nailed in tight, they are somewhat structural, make the building stiffer and safer while the workers are on there, and keep everything at a set distance. So you can use wooden spreaders or wooden layout boards, or you can use these truss spreaders as needed. Here's a house after the second day of construction. We've still got our diagonal bracing everywhere, holding everything secure, but the workers have started putting in all the blocking, which is the next step once all the trusses are raised. We've got our shear blocking on the bottom, our shear blocking at the top, and then the support blocking for the Tyvek, and that also keeps the foam from boiling out, has been added to the bottom here. It's a 2x6. The idea is you would run a continuous row of staples along the bottom to keep that Tyvek from blowing away when the foam gets sprayed against it. The same thing happens above, except with a 2x10, and that goes in up there. So I'm just standing here on some sheathing that's been laid down temporarily as to provide a working surface on top of the floor. Once that roof is on and the building's dried in, one of the next things you can do is add that underfloor sheathing if you'll be insulating from above. That'll really help stiffen the structure. Once again, anything you can add that makes the structure stiffer will make the structure safer. Remember, this house is not sheathed as we would sheathe a conventional house. It's just braced with diagonal bracing. And until we start getting roof sheathing on there, underfloor sheathing, subfloor and wall sheathing, this house will be very vulnerable to wind loading and racking. People working on top of the house are going to be moving those trusses. They have to be very well braced. They should be braced from both ends so the braces are working against one another. The walls themselves should be braced as we've covered. Most importantly, when you're moving plywood onto the roof, do not take a full unit of sheet goods and set it in one stack. You're creating a tremendous point load of several thousand pounds on only one or two trusses that are not braced and shear nailed together to take that kind of weight. It's much safer if the workers on the roof spread out the load and only hand up a few sheets at once. And when anybody is working on the roof, make sure that the structure underneath is well braced diagonally. All the framing has been completed at this point on this house, and the exterior weather barrier has been put on. The house is dried in. It's ready for spray foam insulation on the interior, and on the exterior the siding's going on. So let's take a look at some of the details. Here we're looking at the siding. It's going about halfway up the wall, and this is a good point to talk about how this wall manages weather, because the space between the furring strip is screened and open to the air at the bottom, and it's open at the top in the soffit. What we've created is a pressure equalized rain screen. And what that means is, when you have siding overlapping and any rainwater gets back here, you've got wind driving that rainwater through small joints and imperfections in the siding. Well, as soon as that driving force hits this open chamber between the 1x4s, it's negated. You lose that pressure. So the water stops right back here and it drains here on this house wrap drainage plane down and out, and you have a drying path in this airspace behind the siding. This is ideal for protecting a structure like this from weather. This structure is dried in, the walls are wrapped, everything is nice and tight. It's just about ready for spray foam. One thing to remember here is the underfloor sheathing is in place. This floor will be sprayed from above, and at this point, before the sprayer gets started, it's not a bad idea to run 3 or 4 rows at minimum of 2x4 spreaders, and those should start at the gable end wall and maintain that truss layout on 2-foot centers. Like I said, 3 or 4 rows across this floor would be a good idea. Even just sitting here, I can see several of these bottom cords on these trusses are bowed out about 3/4 of an inch. In addition, the foam can expand and push these trusses out of plumb. If we brace them on layout and then they're sprayed, they'll have a much better chance of lining up on edge when the subfloor goes down. We'll maintain good layout. It's quick and easy to do, and it can buy you a lot of labor savings and peace of mind later when you're putting the subfloor on. One detail around the windows, here they've been wrapped in house wrap across the inside face to prevent any overspray from getting against the window or inside the window opening. But the house wrap here should be stapled back so that the spray foam gets sprayed against the outside here and goes all the way to this inside edge, because we want this window box to stay warm all the way to the inside edge, not just have the foam stop halfway as it does everywhere else. It's very important that the interior of this window opening stays well insulated so we don't attract condensation. Once this house has been spray foamed and the walls, roof, and floor are all tied together with a continuous layer of about 9 inches of spray foam, then the rest of the house gets built pretty much as normal. The remaining space in the floor and in the walls on the warm side becomes available for running mechanical systems. The only difference here is that instead of using drywall as a wall covering, we're using 1/2-inch AC plywood, and it will nail into our shear blocking at the bottom of the wall and at the top. And that's how we get the structural rigidity designed to resist some very high wind loads in certain regions. The sheathing nails in at the bottom and nails in at the top. The entire wall now acts as a shear diaphragm. Here in the state of Alaska, we are building some of the tightest houses in the world, particularly the further north we go. And the reason for this is our energy costs have gotten extremely high. And so we follow a philosophy that is build tight, ventilate right. And so we are using what we consider to be climate appropriate amounts of insulation, lots of insulation in this case, and a high degree of air tightness because air leakage equals energy costs. But that comes at a price because now we no longer have leaky houses that we can depend on natural air leakage rates to keep the occupants inside healthy and to manage indoor humidity levels in wintertime. Keep in mind, in a cold state such as Alaska, the occupants spend much of their time indoors, and so having fresh air becomes very critical in a tight house. When we say build tight, ventilate right, what we want to do is control the airflows going into that house so we're introducing just enough fresh air that the occupants stay healthy, but that we're not overventilating and incurring an energy penalty because we're moving more air, heated air, out of that house than we need to. At this point in time, in the state of Alaska, heat recovery ventilation systems, HRV systems in short, are generally considered the best way to mechanically ventilate a house, whether it's new construction or existing construction that's undergoing a retrofit. In any case, what we have here is a typical example of an HRV system. So we're going to open this guy up and take a look and see what's going on inside. Although this may look complicated, in operation and in principle, the HRV system is actually fairly straightforward. All HRV systems will have 1 or 2 fans, and they will have ducts on either side, or top and bottom typically. But the idea is we have an insulated duct that goes to the outside that brings in cold, fresh air. It's insulated so the duct doesn't attract condensation on the exterior. And we have another insulated duct that exhausts heated, stale air. It's also insulated, so in some cases we may attract condensation on the interior. In either case, we're bringing in fresh air from outside and we're exhausting stale indoor air outside, and those are the insulated ducts. Where the magic happens, though, is here in the core. And so when we look at the core, here's another example, the core will have a series of plates, and they may be aluminum, they may be plastic, or in some cases paper. But what we're seeing is, as the air flows through the core, we'll go back here again and actually look at this core here, we've got cold incoming air, and it will flow on one side of the plates. At the same time, we're exhausting heated, stale air, and it's flowing on the other side of that plate. So alternating plates are incoming and outgoing air. The way we recover heat is the outgoing air, the exhaust air from inside the house, heats up the plate, which in turn heats up that incoming air, and that's how we're recovering heat from our exhaust air. Once our incoming air has been preheated by the outgoing air, it can then get distributed to all the living spaces in the house. So typically your bedrooms and your living room will have a duct with a diffuser that provides fresh air. All the places in the house where stale air gets produced, or humid air, such as the bathroom or the laundry room or the kitchen, they will typically have an exhaust duct that's pulling stale air and exhausting it out through the house via this core. And this leads us to the BrHEAThe system. And what we have done is, when we've created a super insulated house like the integrated truss house with 9 inches, give or take, of spray foam insulation, all of a sudden our heat demand has gotten so low that we can use the low airflows from an HRV system, which will be somewhere between typically 50 and maybe 90 CFM, but because the house is so well insulated, we can actually heat this air even further and use the HRV as the distribution system for heated air. So not only are we ventilating, but we're also heating the house with a system that uses an HRV as a key component.
Here we have a situation in the village where we want to integrate our ventilation. We want to make sure these people are getting fresh air. We also make sure they stay warm. And we want to combine them because we don't want the situation where people turn the heat on and turn off the HRVs. And this makes it impossible for that to happen, because if If your HRV's on, then you're going to get airflow across this heat exchanger, and you're going to have a warm house. If the HRV's off, you're not going to get any heat in that house in an effective manner. The first thing is the HRV, the heat recovery ventilator, and in our case, we're using this little Venmar Eco, and we have it set up here to kind of do a bench test in the shop. We bring our cold, fresh air from outside. We recover some of the heat that would be coming from the inside going out, and now this is supply air that would normally go to all of the rooms in the house. But we're doing something a little different here. We're bringing it into this filter box. This is just a place we can filter out the air. And then right inside here, there's a heat exchanger in here, kind of like a radiator in your car. And the idea is that if we pump hot water through this heat exchanger, then it's just going to warm the air that moves across that heat exchanger from, say, 40 degrees Fahrenheit to maybe 90 or 100 degrees Fahrenheit. So now we've got this warm air, and it's delivered to your room. What's heating it is this modulating condensing boiler. It has the ability to produce hot water and space heating. It provides it at low temperature. Generally, it's low temperature fluid, and since we live in this house is going to be a house with low heating loads, we can take the low temperature water. People find reasons not to use heat recovery ventilators, and it's something that needs to be done, in my opinion. Especially in Alaska, where we're starting to get tighter and tighter houses. We're getting less and less fresh air through infiltration, so we got to bring in mechanical ventilation. Instead of just bringing in cold fresh air, let's go ahead and recover that heat. So we're kind of killing two birds with one stone.
Coming in at 25, going in at 58. How's it feel? It says it's 139 air temperature.
Feels warm.